Hey everybody, welcome to 7b, chapter 7.2. Okay, so here we are going to use what we learned last lesson in terms of similar triangles, and we're going to solve these similar triangles. Okay, so let's take a look at the first example. To determine the width of a river, Chris finds a willow tree and a maple tree that are directly across each other on opposite shores. Maple, willow. Using a third tree on the shoreline, right here, B, the sumac, Chris plants two stakes, A and B. So here are two stakes. And measures the distances shown. So Chris is on this side, okay, realizes that these two are directly opposite to each other, and then he plants a stake there, okay, and there's a tree there. So what he decides to do is measure from the first stake to the maple and finds that it's 24 meters. Then he measures from B to the sumac, the stake from the sumac, and finds out that's 9.3. Okay, and then this third stake he places directly so that it's parallel to this line, and he measures that to be 8.4. Find the width of the river using this following information. So his job is to find out what this distance is. Okay, now how are we going to do that? Well, first off, let's check if these are similar triangles. So, I can see here, angle, A, let's call this S for sumac, ASB, the triangle ASB is equal to angle WMB. Angle WMB. They are both 90 degrees. Okay, WMB. We also know that angle SBA, angle SBA is the same as MBW, MBW, which is also 90 degrees. So because of AA, triangle ABS is similar. So ABS is similar to WBM, triangle WBM. Okay, so since they're similar, because they're similar, I know that the ratio of the sides will be the same. Okay, so because they're similar, I know the ratio of the sides are the same. Because it satisfies AA, it's also going to satisfy SSS and also SAS. Okay, now since we're trying to find a side, it probably makes sense to look at the ratio of the sides. Okay, so which means if I were to overlap this triangle over here, so let's use a different color so it doesn't get confusing. So if I were to take this triangle and move it over here, okay, so if I took this point A and moved it here, A, and then B would be this point right here, and this corner, the 90 degrees here, that would be my S, right? Why did I do that? Just to compare the sides, okay? Because I know the side between B and S, this is 9.3, which means I can look at the ratio of BS over BM. So BS is 9.3, BM is 24. Now this will also equal then the ratio of, now I know what's AS, that's 8.4. Okay, so that means I will know that I can compare 9.3 divided by 24, 9.3 on the small triangle divided by 24 of the big triangle is equal to 8.4 of the small triangle divided by X of the big triangle. Okay, now here I can solve for X and I'm done. Okay, so let's cross multiply. So I have 9.3 times X is equal to 8.4 times 24. So then X would just equal to 8.4 times 24 divided by 9.3, x equals 2, 8.4 times 24 divided by 9.3. 21.68. So therefore, the width of the river is 21.68 meters wide. Okay, and I'm done. So let's take a look at the next example. What is the relationship between the areas in each pair of similar figures? So the fact that I've told you they're similar means that the ratios are the same. Okay? So in this case, let's see. I know from 4 to 8, I need to multiply by 2, right? From 3 to 6, again by 2, 5 to 10, by 2. So I know my scale factor is 2. Scale factor equals to 2. Okay? Now, I'm looking at the areas though. I want to know what's the relationship between the areas. So I'm going to use this one. So the area of the first one is equal to 3 times base times height divided by 2, which will equal to 12 divided by 2, 6 units squared. Okay. Now what's the area of the big one? This one. So the area of the pink one will be 8 times 6 divided by 2. 8 times 6 is 48, divided by 2 is 24 units squared. So obviously we're trying to see if there's a relationship between the scale factor and the areas. So before I kind of conclude with this, or come up with a conclusion, let's look at the second example. Well, what's the scale factor here? Well, that looks like it's times 4, and that looks like it's times 4. Okay? So let's look at the area of the little guy. So the area of that will be, well, just length times width. 3 times 2 equals 6. Let's look at the area of the big one. So the area of the big one will be 8 times 12 equals 96. Do you see a pattern? Well, let's take a look. I'm going to use a different color. From 6 to 24, we had to multiply by 4, right? But where do we get 4? Well, times 2 squared. And where did I get 2 from? The scale factor. Okay, let's see if it works here. From 9 times what? Will get me 96. Well, 9 times 16 will. Well, how do I get 16? Times 4 squared. And so 9 times 16 is 96. So in other words, so therefore, the scale factor squared, so therefore, let's say the scale factor is k. Okay. Therefore, for similar triangles, if triangle ABC has a scale factor of k, okay, so in this case k, then the area then the new area will be k squared times bigger. Not the greatest wording. For similar triangles, the triangle ABC has a scale factor of k, then the new area will be k squared times bigger. Okay? So for example, if the scale factor we realized was times 3, then I know the area will be times 3 squared bigger. If the scale factor was maybe times 5, then I know the area will be times 5 squared bigger. Okay? Last question. Find the area of the industrial zone. Well, first off, let's see if these two are similar. So I know that these two angles are the same. Let's label the triangles. A, B, C. Let's call this EF. Okay, so I know angle ABC, angle ABC angle ABC is the same as angle FBE. Okay. Now, do we know any other angles that are the same? Let me just check. So those we can't. Oh, right. Okay. Now, this drawing is actually pretty poor. I forgot to include parallel lines. Okay. So, assuming that these two lines are parallel, so if these two lines are parallel, thinking back to grade 9, you remember the Z pattern? If these two lines are parallel, then this armpit of the Z, where's the Z? So there's Z right there. Boom. 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 Then the armpits, then those angles would be the same, right? So then angle FEB is the same as angle CAB. So therefore, they are similar. They are similar. So then if they are similar, then I can look at the scale factor. So obviously we're looking at AC over EF, which is for comparing from 1 to 3. Okay. Actually, you know what? Sorry, I'm going to rewrite this as EF over AC. I'm going to put the bigger one on top because EF is 3 and AC is 1. That means our scale factor is 3. Therefore, scale factor equals to 3. Now, scale factor is 3. So I'm going to look at the area of the small triangle. So area of triangle ABC is equal to base, which is 1, times height, which is 1.4. Height right there, 1.4, divided by 2. So that means the area would be 0.7 kilometers squared. So then the area of the industrial zone, which I'll use red, so area of industrial, will be equal to 0.7 times, what was the scale factor? 3 squared. And that will equal to, I believe, 6.3. Just going to double check. Yep. 6.3 kilometers squared. Okay, awesome. So all these questions, your first step is to verify that it is similar, and then you can apply any of the properties of similar triangles. Okay, awesome. All right, take care, guys.